Hello and welcome to our Physics for Future podcast series that we are recording because on the 14th and 15th of May in Luxembourg, we have this amazing conference called Physics for Future. And some of our future speakers agreed to also talk to us to tell you a little bit what they'll be talking about and what they specialize in. And our guest today is Professor Tess Smidt, who is assistant professor in EECS at MIT. As an undergraduate at MIT majoring in physics and minoring in architecture, Smidt engineered giant neutrino detectors and created a permanent science art installation on MIT's campus called the Cosmic Ray Chandeliers that I checked many times. We will share the link in the show notes so you can check it too. And all the other amazing projects that Tess is doing, because she did major in physics, got her PhD degree in physics, but right now she specializes in, can I say that, Euclidean symmetry in neural networks?
Perfect.
Yes.
Yeah, well done.
Okay, good. Perfect. So I passed the first test because it was very difficult to shorten it correctly, Tess, thank you so much for coming today.
Thank you for having me. It's such a pleasure to chat with you.
So I spent a little bit of time on your website, and one of the things I discovered that we just discussed before recording is that you used to have a podcast and you were trying to understand how your guests think. So actually, I wanted to start with that. When you were trying to understand the model of people's thinking, did you ask yourself that question first? How do I think? How do I come to a conclusion or to an idea?
Absolutely. I think asking ourselves kind of that metacognition, or just the term that people use to say, okay, how do I think about how I'm thinking, is just such a interesting and fun question to ask oneself. And it's so difficult because you're interrogating the thing that's doing the thinking. So I actually read a lot of business books and psychology books, and it's been something that I've always been interested in. I'm reading more about sociology to understand from the humanities, how do you do the type of interviewing one does for either anthropological studies or modern sociological studies. So it's actually something that it's not my profession, but it is something that I am passionate about and try to educate myself in. So that's, something that I strive towards, but it is very challenging.
When I was introducing you, I said that you started with physics, there was a bit of architecture, and now it's neural networks, so computer science and all that. Is it actually a close move from physics to that, and physics and architecture actually, or not?
It's a great question. I think, again, I do like seeing the connections between things, and I do like to think about, this goes back to the modeling, how people think. What are the different abstractions that people use in different fields, and what's kind of the glossary between them? Like, okay, they call it this in this field, but they call it this in this field. And okay, maybe it's not quite the same idea, but it's like the same idea with this little twist on it because they think about this other thing this way. So following the chain of things, I think that has made it easy for me to switch into various fields and have beginner's mind and just kind of try different things. But I usually would switch fields because there was something specific I wanted to do. I was like, oh, I'm now obsessed with, in the case of getting into neural networks, I was just very frustrated that there weren't neural networks that faithfully treated the types of data that I was working on. So back in my PhD, I was running big quantum mechanical calculations on like atomic structures. So just think of points in space. So I have my points in space. I put them into a computer program that runs on a big supercomputer, and out comes some descriptions of kind of what's the physics that's going on at the quantum mechanical level. So kind of a complicated calculation, but mostly it's that it was slow. And so with neural networks, I think one thing that people hope in physics is to create either digital twins or surrogate models. These are like the catchphrases, but essentially the thing that takes our calculation that was really slow and makes it faster. So we don't have to wait so long to get feedback from the types of calculations we're doing. And so that was my main motivation, but the neural networks couldn't handle 3D geometry. And I'm like, this 3D geometry is pretty general. So it seems like it was worth making a neural network that could understand 3D geometry. So that was my motivation. So I switch fields whenever I get frustrated enough that I'm like, I need to go over here to fix the thing and where I'm at. That's kind of my motivation for field hopping.
Interesting, for sure, because there are two challenges I see. And the first one is the one you mentioned, the glossary, right? So whenever I talk to people who specialize in interdisciplinary research, they are kind of saying, okay, first we sit down with the other, and then we kind of try to align the terms because we don't speak the same language, right? So I think in the beginning probably it was also challenging for you. Okay, here I am, I'm talking computer science and this is clear, but then the people are like, oh, that's what the physicists say, not we don't say it here.
Yes, yes. That's such a huge thing. And I think it's, technical jargon or, just these technical terms that people use, they are very useful, but they can also be a bit insidious because sometimes if you use a word for long enough, you forget what it actually means or where did it come from. So this is actually a big thing in my research group. So I have a research group that's very diverse on multiple fronts. So not only from where people are and, their nationality, their background, different values they hold very dear, but also just technically, like they're from very different fields. And I really love the culture this sort of induces in the group where we have to be able to speak both the technical language to communicate with people in our field, and we have to be able to say it plainly while still maintaining the richness of what we're doing. And so I think that active translation is actually super helpful for the students. And it also makes their work more impactful. They're able to connect with more students in other fields. I think it's a really useful skill to have, but it's very challenging. So I think getting practice in grad school it seems like they're really benefiting from it. And that's really gratifying to see.
So before we define what you mean when you say certain things, as you said, I just wanted to ask you also another thing, because if you had, quantum mechanics calculations and all that, why didn't you decide to just wait for quantum computers, but you went into neural networks?
Yeah, that's a great question. So yeah, quantum computers are super interesting. It's definitely an area where I don't know enough to, completely give benchmark times of when they're going to be able to do the things that I needed them to do. There is an issue that it's very hard to build quantum computers that have kind of the accuracy you need or can do calculations for long enough to do the types of thing I'm interested in. So some of it is a limitation on the size of quantum computers. And then some of it is also, there are some materials where you could treat them very quantum mechanically and you would get good answers, but sometimes the classical calculation is good enough. Sometimes you use a calculation knowing that parts of it are wrong, but it's still useful because you're using it as sort of a guide. And so this is something that when I first was introduced to, wait, so we know that the calculation is wrong in specific ways? And it's like, yes, but if you have enough experience with the calculations, you know how to sort of read the tea leaves, if you will. So yes, you can get very accurate answers on something like a quantum computer if your system is not too big so that it can fit on the quantum computer. But then sometimes it's also, we have these giant computers and so we can get often the answer we need with the technology we already have. So it's a bit of a balance. Like we want the new tools as well. That's very exciting, but the timeline might be different.
And to listeners, if you want to know more about this, because I don't want to ask you too much, because as you said, this is not your specialization. There are other episodes that you can listen to, and some of the guests that are coming are also specialists in the field. So go check them out also during the conference. Remember, 14th, 15th of May. But you said classical calculations, and I was wondering, neural networks and machine learning, that's classical or not?
Oh, that's a great question. So I think I just meant on classical computers versus quantum computers, even though it's a quantum mechanical calculation on a classical computer, just to make it completely confusing.
Okay, good. I have to say that I do know a little bit about machine learning, but I assume that some of our listeners might be a bit new to this. And in your talk, you're actually going to talk about AI, not machine learning. So let's first once again reiterate, AI is machine learning or not?
Yeah, great question. So if you ask different people, you'll get a different answer, but I'm going to give you my answer. So artificial intelligence is a kind of a big field that has existed for many years. And then we've had sort of different incarnations, so different versions of the field. And so we have machine learning, which was sort of like a rebranding, especially after like an AI winter sort of thing. I think AI is also generally, there's a connotation of dealing with like robotics and agents. So this is why I'm saying like you talk to different people, you'll get a different answer. But I like to think of like AI as the big umbrella, ML is a smaller umbrella, and then deep learning is an even smaller one. And then nothing is clean in this world, like cleanly cut. So there's connections between these things, and people will use the words interchangeably. But deep learning, I would say, is like a specific technique within the realm of machine learning and artificial intelligence.
Okay, so let's leave AI as this overarching term and dig deeper into machine learning. What is it actually?
Yeah, so machine learning generally is a way to write computer programs that can learn to do things from data where you've specified a process for how that program is going to be able to like complete the task. But you're not necessarily like going in there with a bunch of if-then statements specifying every single detail about the program, but rather you have a process by which, with data, the process is able to emulate a desired behavior. And I think that's the big difference is that it's quote unquote learned because it's learning it through the data you give it and the process that's defined.
And then part of it is deep learning.
Yes. So deep learning is the subfield within machine learning that folks are using neural networks. And neural networks sound very fancy, but really the amazing thing is that a neural network is kind of anything. The key thing that makes a neural network work is how we update the parameters inside the neural network. So if I think of a neural network as a box, as we often do, so it has inputs and it has outputs. Now the inputs would be the data, but also these numbers that are like the parameters that are controlling different things in the box. It's hard to interpret exactly what those parameters are doing. That's a whole field into itself. People work on interpretability, but I put a bunch of numbers in that it's going to update and I give it the data. What makes a neural network special is the way that I update the numbers that go into the box, the parameters. For example, I look at what the box outputs and I compare it to what it should have outputted. So let's say I have some training data and I have pairs of inputs and outputs. And then I have my model with its random parameters. We see how well it does. It shouldn't do very well in the beginning. And then I compare them. For example, I subtract them. I take the difference. Maybe I square it. And then this next part requires a bit of calculus. So what I do is I basically ask how much of the error, so how much of the difference between what I got and what I wanted, how much of that can be attributed to each parameter that I put in. And the way that we actually evaluate, the blame, if you will, of like, it's this parameter's fault. It needed to be like, 0.1 bigger or 0.1 smaller. The way that we calculate that is using calculus and using derivatives. And so this whole process, everything inside the box, we have to be able to keep track of these differences. And so we usually use something called an auto differentiation framework for keeping track of this. So we can just focus on writing the program, and then we're able to do this difference procedure automatically. So it's part of the program.
So now you're talking, at least to me, you sound like a mathematician. So you do need a lot of maths as well in order to cross from physics to computer science, or not really?
Well, I would say physics is a pretty good base to do just about anything, because it turns out the physics of our world is pretty crazy. When you learn it, it's completely magical. Like, I don't know if science fiction can really beat the reality of how physics works. So I would say we learn a lot of math when we are taught physics because we need that language to articulate the complexity of what's around us. And in computer science, you also require lots of maths. Computer science culturally stems more from math, and then physics is kind of its own thing. And like electrical engineering actually stems more from physics in some ways, at least culturally. There's a lot of math there too. So I think the math you learn in physics is very helpful for computer science. But there's also a different view, even of the same topic. Like you could be talking about the same math from a completely different angle. And so even how you like process your result or like how you interpret your result can be very, you look at it through a certain lens. So that's very interesting. I've been enjoying better understanding how my CS colleagues think.
Yeah, for sure. It sounds very, very interesting to me as well. I got you to talk about maths, but now coming back to the neural networks and all that. So you said we have data, we put it in the box, and then it gets out and it kind of keeps getting updated, or rather not updated, but perfected if you want.
Hopefully.
And hopefully, exactly, because it's not always like that, I know. But that's the holy grail, let's put it like that. And in the meantime, we look at the data, right? And of course, there's all the bias in data and, bad data that goes in and all that. But there's also the problem that you're looking at is that certain data is not so great for neural networks.
That's correct. So there's many different things that can go on when you're setting up problems. This is something that I teach. I teach Introduction to Machine Learning. So this is something that with the students, kind of getting a handle on all these different factors that can make a machine learning problem well posed or not. Like, does it even make sense to do machine learning? How do you represent the world into this rather simplistic program? So thinking about, if I want to predict what's in an image, how do I represent that? How do I represent the label cat and dog and cabinet and book? And usually we do something very simplistic. Like we have just a string of numbers, and if it's a cat, it's 1 0 0 0 0, or if it's a dog, it's 0 1 0 0, or if it's a bookshelf, it's so there's like no inherent order. We're kind of losing a lot of information, but in fact, that is typically how these things are encoded. Now, when we do like language models, which is a whole nother topic, we have different approaches for embedding words and things. But yeah, it's a huge question of how do you actually represent the problem to the model? And so there's this whole area within deep learning, so within neural networks, called geometric deep learning, which is the field that I'm in, which focuses on how do we represent things like surfaces. Like imagine you have some cartoon character and you have a mesh representation of that character and you're going to put textures on it or something. Like, okay, so how do we represent the mesh to the neural network? How do we represent shapes and 3D scenes? Like if I'm looking out upon a scene, how do I kind of convey that to the neural network? So there's a lot of craft that goes into building the program that you then use for training. So what types of interactions can the data have with itself, or the parameters in the data? So we're really the architects of these interactions and the architects of how are we updating the parameters? How do we say this is a good or a bad output? We typically have like more nuanced ways of defining this like loss function or this error function that is determining how we're updating the weights. So there's a lot of knobs. So it becomes very much an art form as much of a science or an engineering problem.
When I was preparing for our discussion, what totally blew my mind, except for the fact that, of course, for us, describing the world to the computers is tricky, just like, in computer vision, trying to make them see something. It's yet another field, right? But the whole idea, what you're talking about, that it's just enough, let's say you have a molecule and you turn it around and then the computer will not think it's the same molecule. It's just so crazy, isn't it?
Yes, it's something that, again, talking about like one's own bias, like as a human, we're very comfortable with things rotating. As children, we learn how to kind of navigate 3D space. There's a lot that's actually built into our brain from the get-go about spatial reasoning that we don't have to learn. It's just in there. So, we forget that actually something needs to learn that if I rotate this object, it's still the same thing. And this is something that's so fundamental to physics, but the neural network doesn't know it. So you can train it to do it. You can train it to learn this. But what's interesting is that there's so many consequences to the fact that in physics, if I rotate things, physics still acts the same. It's actually a very deep aspect of physics is that you have these symmetries of, you can run the same experiment at a different point in time and you're going to get the same answer. The fact that you can, move just linearly in space. I can just move from point A to point B. I'm not, rotating or anything. And the physics should not change. These are very deep things about physics. And they're quite simple assumptions to make about your data, but they have very deep consequences. And so I'm very interested in if you actually faithfully treat these deceptively simple aspects of your data, how does that impact how well you can learn from the data? How much easier does that make the task for the neural network? How much harder does it make the task for the neural network? I don't know, because then there's questions of, is it harder to optimize a black box that now has to preserve symmetry? So this is all open questions. So far, it seems like they actually do very well when you give them the symmetry, when you tell them that, okay, if you rotate it, it's still the same thing. If you translate it, it's still the same thing. But there's also like weird properties that come up, like the way that you articulate like a task. So you can say, oh, I want you to take this collection of points and I want you to group this one in group A and this one in group B. Well, if those two groups of points look the same, if you rotate them, a neural network that's built to protect and preserve symmetry can't do it. But it's not because it's a bad assumption, it's because you articulated it in a way that violated symmetry. So there's a bunch of interesting consequences that can makes your life in the short term a little bit harder, but in the long term, it has really helped me ask better questions or pose better ways to ask the neural network to help me out with a task. And it's actually taught me things. So I think, I'm training it, but it's also training me. So it's a little bit of a symbiotic relationship.
So you're the human in the loop that we talk about, right?
I am the human in the loop. Yes. I think we're all humans in the loop. I think there's a lot of stuff that is much more hands-on than maybe is publicly perceived. Just the amount of human labor that goes into training a neural network is just so much. Really, the only reason to use a neural network is like if you have no other option, like there is no other algorithm that will work, or the algorithm you have is too slow in my case for many things. But it's extremely labor intensive. We're getting better at it, but it's when you're doing something new with neural networks, it's very labor intensive to figure out how to train it properly, how to figure out what weird idiosyncrasies it has. Like, oh, why is it predicting, carrot when it should be predicting caterpillar? Like, I don't know. We have to figure that out. Why is it doing that?
I was just wondering also on the application side. So why do I need to recognize 3D objects through neural networks in the data set? So why is it important for me?
Yeah, so there's lots of different applications in which you want some sort of 3D recognition. So maybe a practical one would be like self-driving cars. Now, hopefully the car is usually upright. It's not upside down. We're not turning the car all, hopefully everything's going well. However, you could imagine it needing to recognize a certain object. So they have like these little laser sensors that send out light and are able to detect things in 3D space. It can be helpful to have the guarantee that it's going to identify the thing in different orientations and not be thrown off. That if I rotate something and the neural network hasn't necessarily been trained to perceive things as the same thing if it's rotated, it could have some sort of erratic behavior that could be concerning. Now, there's a lot of training data that goes into driverless cars. So I think that they've addressed this through just lots of data so that eventually it gets used to seeing things. But it's a nice guarantee to have so that if you build the rotation symmetry or translation symmetry into the model, you don't have to add more training data for that. Like it's going to get it the first time. In the case of science, this is particularly desirable because scientists we have a high bar for safety in driverless cars, but like for numerical things, scientists have a very high bar. We like to know that the answer wasn't going to change just because I rotated the object. So we like to have that guarantee because that's how our physics simulations work, where had I rotated or translated things, it's still going to give me the same answer or the same answer rotated or the same answer translated. And so we like these guarantees when we do science.
Yeah, good point. And that also, I guess, goes into, protein folding, so chemistry, drug design, all these things when we have 3D objects that we're rotating, right?
Yeah, absolutely. And again, people take different approaches. So I find it really interesting to build the symmetry in and see the consequences. But we also do things where we see how does it learn the symmetry if it's not originally told to obey symmetry. And so there's kind of a discussion in the community of when does it make sense to just learn from data and when does it make sense to build it in. For me, I think we must do both. You kind of have to explore all your options, and they often inform each other, because if your network has learned how physics operates, it has implicitly learned the symmetry. Maybe it learned it in sort of a different way than how we would put it in by hand, but then you want to kind of compare. So you need both. So I find it very exciting to have something that we can check, because there's a lot of concepts that are not as mathematically well defined, so we can't build them into the network and compare it. So it also makes an interesting approach for interrogating how did the model learn this and how did that differ from maybe our expectations. There's many different layers of it, which keeps me very occupied and entertained.
Until you get very frustrated and then you switch again into something
and
else.
then I switch fields. Yeah, you never know what the next thing
Which is very tricky, because the next question I wanted to ask you is how do you see the development of your field in the next 10 years, let's say, from now?
Yeah.
Because who knows where you'll be, but let's assume you're staying where you are.
For sure. So there's so many wonderful people in my field. And so I think there's many exciting directions. So maybe I'll kind of broaden for just geometric deep learning. I believe that, our ability to build design tools that are aided by AI will just be enhanced, that it'll be much easier to articulate. Let's say you're making maybe like a sculpture and there's you want to add some texture to it or something. You're able to just use words to describe kind of how you want to go about this. Or I think one of the great things about programming in general or computer science in general is ideally it should help make it easier for us to articulate what we want to do. And so I think that's really the big benefit is in 10 years, things that would normally take us hours to articulate through computer aided design. And it's very laborious. It's very intensive. And if we can make that process just streamlined, more intuitive, and still get to where the human was intending to go, that's a huge win. So you can focus on more of the fun aspects of the creative process versus some of the more annoying aspects of CAD modeling. So that's some specific aspects of where I think at least geometric deep learning for kind of computer-aided design is going. But I also think that just the role that geometric deep learning will play in physics simulations, in the design and engineering of physical systems is going to be quite immense. Already folks are using this for doing drug design, for understanding protein interactions. So I would imagine that we're going to have amazing multi-scale physics models, things that can model things at the small scale, the medium scale, and the large scale all at once, treat systems holistically, allow us to zoom in where we want to zoom in or zoom out where we want to zoom out. So to be able to just digest complex physical systems in a way that currently is just so hard to do, just because the tools, you use different tools at different length scales, and it's nearly impossible to really get a coherent, holistic picture. So I think just the ability to explore and understand things will be really enhanced.
Yes, for sure. And if you want to know more about what is possible right now, remember Tess will be here in Luxembourg on the 14th and 15th. I don't know whether you'll be there on the 15th, but on the 14th, for sure, you'll have a talk. So you can go and check it out. And it's about harnessing, so as you're saying, the difficult thing, right? Harnessing symmetry, which Tess will be talking about. But, we jumped into future because it's physics for future, talking future and all that. But I have a very difficult question. I'm very happy I don't need to answer this, but you will have to.
Okay.
Which is going to the past, So the last, I don't know, you can choose last 20 years, last 50 years, one, two most groundbreaking for you discoveries in science and technology. What was that? What was for you just the thing, or maybe people that were important for science?
Oh, goodness. It's a great question. This is definitely where I wish my history of science was a bit stronger. But, it's interesting because sometimes science takes a while to percolate into technology and society. There's so many amazing things that, especially when I talk to my grandma about technologies that she witnessed evolve in her lifetime and just how that's changed her quality of life or the quality of life of others. A lot of them will stem in the sciences, but maybe instead of 50 years, we're talking 75 years or something like that. So it can be longer. I certainly think just the advances in medical diagnostics is just really phenomenal. So our understanding of more fundamentally what's going on. I mean, look at mRNA vaccines, just our ability to have more control over how, this battle we have with nature. So I think that's really amazing. I think the advances in understanding the dynamics that affect climate dynamics or just fluid dynamics for engineering. There's so many interesting, very fundamental physics problems and modeling things like turbulence. It's super fascinating. I mean, there's always going to be talking about the miniaturization of the transistor leading to things like smartphones. And I mean, that's incredible, right? The semiconductor industry, truly incredible. But then you look at the infrastructure required for cell phones to exist, like, all these like network cables, undersea cables, like the whole evolution of undersea cables is actually a fascinating history. Telecommunications and satellite. It's just all of this stuff requires, relativity and other things. It's quite tremendous. And then you look at some things that are maybe a little bit more humble, but no less impactful, like the advent of the shipping container and the ability for doing logistics and tracking and having RFID tags on everything, and the ability to keep track of where everything is and process things coming into ports and put them on trucks and track that. And I mean, that is a huge mathematical problem. Like logistics is so completely fascinating, just operations research in general and things. So man, okay, I'm really I'm really giving you way too many answers here, but it's just super tremendous, like how much things have changed in the, past, I don't know, 50, 100 years.
Totally.
I can't really give you one single thing.
And just to wrap up, I don't know how many you gave me, but a lot of different things that changed. For sure, what we will be focusing on is not the past, but the future. Once again, as I said, so if you want to know a little bit more about what Tess told us today and what she specializes in, remember the conference. And what remains is to thank you very much for today.
Oh my gosh, this is such a fun conversation. Thank you for having me.
Physics for Future is organized by the Department of Physics and Materials Science at FSTM of the University of Luxembourg. Come join us on the 14th and 15th of May in Luxembourg. More information in the show notes.